All right, so working through some more of these problems. We're on to number 12. We got through 11 yesterday. They gave us E cell for this thing. This is kind of car battery stuff, right? They use 6 cells. You'll notice that the E's for these cells are not all that high, right? 2 volts is not a ton. Well, 2 volts is not going to start a car. So you have to put several of those together in order to do that, which is basically the same way you get 9-volt batteries, right? As you put 6 1.5-volt batteries in series. So when you want higher voltages with batteries, you just put more of them in series because you're not going to get a lot better than 1 or 2 volts with chemical reactions. You look at some of the better batteries like lithium and stuff, and you look at the cell potentials for lithium, they're a little higher. So that's one of the reasons that lithium batteries are a little better. You don't need quite as many of them in series and stuff to get more power and that kind of stuff. But anyway, when I see delta G and E, that is our Gibbs free energy relationship, which is just this, right? Remember our Gibbs free energy is our maximum work. And so we say, well, the number of electrons transferred in this thing times Faraday's constant. Is that Faraday's constant? Now I'm drawing a blank. Whatever. It's that 96,500 number. Yeah, that's Faraday's constant. Yeah, that's Faraday's constant. And our standard cell potential, right? So our delta G is going to be number of electrons transferred. So let's figure that out in one of these guys. So this is a whole balanced reaction here. So I can say, well, my lead is going from lead to lead plus 2. So this appears to go from 0 to plus 2. And this is minus 4. So a plus 2 or plus 4. This appears to be lead 4 going to lead plus 2. So both those appear to definitely be 2 electrons transferring in that. So we're going to go ahead and put a 2 here, times the 96,500, what are the units on that? Coulombs per mole or volts per mole. Well, joule volts per mole. Yeah, that would probably be a better way to do it. Joules per volt. Then stuff cancels a little easier. And our electrochemical cell is 2.04 volts, right? So then we say 2 times 2.04 times 96,500, and our delta G in terms of joules, not kilojoules, is 393,720 joules per mole. So they're probably going to be in terms of kilojoules. So then that's going to be 1, 2, 3. And I was sloppy with my See, this is don't be sloppy like Mr. Fred. I missed my negative right there at the beginning, because if I have a positive E, that is spontaneous, so that should correspond to a negative delta G. I'm pretty good about going back and saying, does this make sense? But I drop negatives and stuff, right? So be careful on that. I just did on this one. So it gives me a negative 394 kilojoules is our delta G for that, right? So that's 12. 13. Move this stuff around a little bit. So let's see. The standard free energies of formations for several species are shown. What is the standard reduction potential for methanoic acid if in this solution? So they've given us some delta G's. Looks like what they're wanting us to do is work the exact opposite direction of what we just did. So we're going to do products minus reactants. Remember, for delta G's, amounts do matter and stuff. So we're going to go products. So negative 351. Is this thing balanced? This appears to be balanced. Plus a negative 237. So that's my products minus my reactants. So 4 times 0. There's like a big parentheses there, or a bracket or whatever. And this, did I go in the wrong spot? I went in the wrong spot there. Negative 163. I wasn't looking closely on that. That's my product. My reactant is this negative 351. So minus 351. So plus that negative 351. Is that times anything? No, it's not. So my delta G for this thing is going to be negative 163 minus 237. So that's a negative 400 for my products. Minus this, that's plus 351. So plus 351, so that's going to be 49. So it's a negative 49 kilojoules, right? So negative 49,000 joules is my delta G. Oh, you can't see where I'm writing there. My delta G is negative 49,000 joules. So if I do that, delta G equals negative NFE, I should have a positive voltage. So if I'm, just scrap those negative voltages there, right? Because I've got a negative delta G. So negative 49,000 divided by negative 1, so it's going to be a positive 49,000, divided by Faraday's constant, divided by the number of electrons here. Well, they went ahead and showed me the number of electrons, so that's nice. So 49,000 divided by 4 divided by 96,500 is going to give me 0.126, so 0.13 for that one, right? So A is the answer on that one. Just work in the opposite direction on that. Let's see, 14. If you could increase the concentration of Ag plus, which would be, okay, so now it's like a conceptual Nernst equation problem, right? So they're saying if we go to a non-standard cell, is this going to become more powerful or less powerful? So basically, if I'm adding to my reactant concentrations, it's going to bump it up. If I add to my product ones, right, just think of it in terms of equilibrium kind of stuff. I know I use like that's like a bad word in this class. So let's see who we need to flip around here. We're going to flip around our copper, right? So that's going to be copper goes to copper plus 2 electrons. So silver ions are a reactant for us, right? Because now that's going to be a negative. So if silver ions are a reactant and they increase the concentration of that, that's going to increase my cell potential, right? My cell potential would increase. If you could increase the concentration of Cu plus 2, which of the following would be true? Well, it would decrease now, right? It's going to decrease because I've already got some there. So when we do our, we could do it from a log point of view, right? This is E standard minus 0.0592 over N times log of Q, and that's products over reactants, right? So if I increase my Q value, right, as my Q gets bigger, that's going to make this more positive, right, which makes this whole thing negative. So then that is going to decrease that, right, because it's products over reactants on that. Q is going to be products over reactants, So as Q gets larger, right, if I take log of 10 instead of log of 1, log of 1 is 0, right? So as I add more to my products, right? So as I add more to my copper, that's going to increase this log value in a positive fashion. I don't know if you can even see that, right? But as Q gets larger, this all remains positive and larger. And so then that negative there is going to make this less. I think it works easier in terms of just thinking about it conceptually. If I have more products, Le Chatelier's principle almost, it's not going to go forward quite as easy. Right? When I started doing the math, I had to stop and rethink it for a second. Okay, a cell is set up with copper and lead electrodes in contact with copper sulfate and lead nitrate, respectively, at 25 degrees Celsius. The standard reduction potentials are there. If sulfuric acid is added to the solution, forming a precipitate of lead sulfate, the cell potential. So this is another Nernst equation, but now we're just saying what's going to happen to this. So we're going to flip this around, right? We're going to flip this around and go from lead to lead plus 2 electrons. And so lead is a product. So if I add something to this, it's going to cause that lead to precipitate, right? So this is going to precipitate our lead out of the solution. That's going to drop my products, which is going to make it easier for the lead to go into solution. So our cell potential will increase there, right? 17, we need like an electroplating one. That's too many Nernst equation. Nernst equation is neat, but this is another Nernst equation one. The answer key I posted on there, but that's just a C, right? That's just Nernst equation. We can handle doing Nernst equation stuff. Let's see, do we have term of the equilibrium constant? Oh, there we go. We could do a nice equilibrium constant one there. So we've got equilibrium constant they're asking for. So we can go right back to our Nernst equation. So I don't think we've worked one of these guys yet. So this is our regular Nernst equation, right? But if we set it equal at specifically at equilibrium, there are some things we know. We know our delta G is 0, and also our electric, if it's at equilibrium, the cells stopped working, right? So that means I can plug 0 in for this and say E standard naught equals negative 0.0591 over N times log of not Q, but log of K, right? So since we're at equilibrium, Q now becomes K because we are at equilibrium there for this one, right? So now we can say, well, E standard, let's see, who do we need to flip around here? We're going to flip around the nickel. No, we're not going to. Is that a minus? Oh, that's just, yeah. Yeah, that is a minus. So we're not going to flip this one around. We're going to flip this one around. So that means we flip this sign. So E standard is going to be positive 0.76 minus 0.23. And I've got to delete something off of my calculator here. There we go. So E standard is 0.53. And then when we move that over, that becomes negative. And so both of those are negative, right? So 0.0591 over N, number of electrons would be 2 here, times log of K. I'm left-handed, so you can never see what I'm writing. So then we just do 0.53 times 2 divided by 0.0591. And so we work from there over to here. So we have 17.9 equals log of K. To get rid of the logs on both sides, we do inverse log, right? 10 to the 17.9. So K equals 7.94 times 10 to the 17th. It's kind of close to that one. Did I make a math error somewhere? 7.9. Oh, I just should have kept more digits on that. 10 raised to the 17.943. Yeah. Yep. I should have just kept a couple of digits. Whenever you're dealing with logs, always keep a bunch of extra digits. So then you get the 8.7. So this guy's 8.6. Right. So A is the right answer there. Okay. On to a little bit easier one there. I will try and make sure and come back and do another couple of those equilibrium ones because we haven't done too many of those. 20, an antique automobile bumper is to be chrome plated, which is dipped in acidic chromate ion. Served as a cathode of an electrode. They gave us molar mass. We know the current is that many amps. How long will it take to deposit that many grams? So this is one of those where I just do this as a unit conversion thing. Don't need to do that in scientific notation. 172 grams of chromium. We know it is going to be 52 grams for every 1 mole. We know for every 1 mole of chromium, let's see what our charge has got to be here. So we've got a plus minus 14, so that must be total of plus 12. So plus 6. For every 1 mole of CR, you're going to have to do 6 electrons. So we're just dealing with 1 CR at a time here because there's 1 CR because this is in terms of moles of just straight chromium. So it's going to be 6 electrons at a time that we're dealing with there. And then for every 1 mole of electrons, it's 96,500 coulombs. And remember, amps is a coulomb per second. So it's 21.4 coulombs for every 1 second. And they've got this in terms of hours and stuff like that. So then I'll convert it to minutes and then hours, depending on what we're looking at. So 172 divided by 52 times 6 times 96,500 divided by 21.4. And that gives us 89,493 seconds. If we divide that by 60, that's going to give us 1,491 minutes. So it's not the minutes one, so we divide that by 60 again. And that gives us 24.85 hours, right? 24.85 hours. So that's here B, 29 hours. Similarly, electrolysis of molten salt with the formula MCl using a current of 3.86 amps for 12 minutes deposits 1.52 grams of the metal. We want to identify it. So I'm thinking molar mass. As soon as I read this, I'm thinking this is the step we're missing right here. Basically, we're going to work backwards and we're going to be able to figure how many moles we're talking about, and then we'll figure molar mass, right? So we'll work backwards. So we say 16.2 minutes times 60 seconds for every 1 minute times, let's see, for every 1 second, it's 3.86 coulombs. For every 96,500 coulombs, it is 1 mole of electrons, right? That's that thing, right? So let's figure out how many moles of electrons we're dealing with first here. So then we can, because there's a charge issue here also, times 60 times 3.86 amps divided by 96,500. So this is 0.03888 moles of electrons. So if it is, almost all of these are only 1 electron. So if it's 1 electron per mole, then all I have to do is take that mass, 1.52, divided by that, and that gives us a molar mass of 39.09. So that's potassium, right? Potassium's molar mass is 39.09. How am I? Calcium's close to that too, but calcium's double electrons. Yeah, 39.09. So that's potassium. So calcium's not going to be a great option here because that would need 2 moles of electrons for each one. So that would only give you half as much metal, right? So if I could, since you need 2 electrons for each one, that'd give you half as much metal. So there's 21 would be potassium. Anyway, hopefully, that got to be 18 minutes. That's long. Oh, well, it's Friday. You've got nothing else to do.